Okay. Awesome. Yeah, so I've been with Microsoft for the past almost 4 years, working on responsible AI only for the last year or so, but within Azure Machine Learning, if you've heard of that, for the last 2.5 years. And we call it responsible AI. Other people like to refer to it as ethical AI or ethics in AI. There are a lot of topics. Fairness is one of them. We have some people working on machine learning interpretability, sort of to understand what your machine learning model does at all. Some people working on differential privacy, confidential machine learning, safe machine learning. So there are a lot of topics, some of which came up here already in the introductions, which is fantastic. But I'm really going to focus on fairness only. And I've been told I have 45 minutes, which is ambitious for covering fairness in machine learning. So I'll try to give you a high-level rundown of what's going on in the field, what people are thinking about, and leave you with a few links if you're more interested in certain topics, especially if you're more from the law area, or if you're a computer scientist like me, then you can go dig deeper on those. And yeah, like I said, I'm happy to talk to people afterwards as well, or on other days. More than happy to set up follow-up meetings. So if you weren't there right in the beginning, you might be confused about the second part of what it says here, fairness in machine learning and fair learn. Fair learn is just a toolkit to hopefully mitigate unfairness in your machine learning models, and at the very least assess whether there's any unfairness. Although fairness itself is quite a tricky topic, so we'll get to all of that in the talk. So this is the tool that I work on in my day-to-day life as a software engineer, but it's open source, so I don't feel so bad advertising for it a little bit in the end. But I'll keep that part short. Promise you that much. So I guess after all the fantastic introductions that we've had before, I don't really have to say a lot about the impact of AI anymore. Everybody's familiar with that. It's become really pervasive across all kinds of domains, and certainly in personal life as well. But this comes with issues at times, and some of those are, I'm sure you're familiar with. There are many, many more cases I could list. And in fact, I have a collection of questionable or outright unethical use cases on my website. But these are just a few examples. You have recruiting here, for example. Automated application screening is something that's already in use by many companies today. So you can imagine how if that is a system that treats people unfairly, how that can affect people's lives. On the right side here, we have a screenshot from the ProPublica study on the Compass tool. In case you've heard of this, this is about criminal sentencing and providing risk scores for that, so that judges can decide whether somebody should go to prison or not, or so highly high stakes scenarios, very much. And then at the top we have yeah, pretty much only face recognition, but you can interpret this as perhaps a predictive policing scenario. So it's not always such high stakes scenarios where fairness plays a role, but those are the most important ones. So it's really important that we think about what fairness may mean in such scenarios and how we should think about this. As somebody already brought up right before the talk, what is fairness actually? Can we actually as humans agree on what that is? I agree it's very tricky. It's a societal concept, and I'm perhaps not even the right person to talk about this, because in computer science this is a very recent topic. Other disciplines are much more familiar with fairness, if that's philosophy or law or social science. And as you'd imagine, if you think about fairness, it becomes tricky defining that in a general sense, where it would fit every scenario, and really that cannot be done. There's no one size fits all definition, and that is something that we grapple with a lot when trying to assess fairness in machine learning. A lot of focus has come on bias in machine learning, and I'll get into that as well. There are many papers out there that try to sort of list all kinds of societal biases and other kinds of biases that factor into machine learning and how that manifests itself in outcomes for people. But it's really tricky to actually concretely figure out how a certain kind of bias affected the fairness of your model. So the way we prefer to speak about this and to think about this is actually in harms. So what actually happened to the people who are affected by a certain automated decision. And that's why a few people, I think actually most of them or all of them were from Microsoft Research at the time, came up with this harms framework. So there are pretty much these 5 categories of harms that can be exhibited by a automated decision, and that I'm sure this is no surprise to most of you. There are harms of allocation. You can extend or withhold opportunities, resources, or information. A good example would be the hiring tool that I talked about very briefly in the beginning. So if you screen applicants, then you're either extending or withholding the opportunity to interview for a job. For quality of service, that might mean a system doesn't work as well for me as it works for you, or vice versa. So you can think of this as, for example, a voice assistant working better for native speakers versus non-native speakers because their voice is just not recognized. Stereotyping, I think, is one of the more straightforward ones. There was a news article a while back where I think it actually came from a paper, but somebody translated the sentence "he is a nurse" to Turkish through an online translation tool. And Turkish is a gender-neutral language. So whether you write "he's a nurse" or "she's a nurse" shouldn't make a difference. And then when you translate it back from Turkish into English, it suddenly becomes "she is a nurse." The system is essentially reinforcing this existing societal stereotype and thereby harming, well, in this case, society by reinforcing the stereotype. Denigration is also something that's fairly common, usually something related to hate speech. If you've heard of Microsoft Tay, that is a very good example. Another example is Google Photos, which a while ago mislabeled a picture of a Black woman as a gorilla. They've since done some work to counteract this, but I don't know where they left this after all. And the final one here is over or under representation. Usually this ends up causing harm because already under or overrepresented groups are even more amplified in that effect. So for example, a few years ago, if you had searched on any common search engine for the term CEO, you would have only seen white men. And while there are more white men as CEOs, it was even disproportionately more so in the search results than in reality. So I want to make this very clear. These harms that can happen, it's not that you can only have one. You can easily find AI systems that exhibit multiple of these, unfortunately. It's not just one, but it's important to think about how they harm people so that we realize whether we actually want such a system or what to do about it. And then when we think about who actually suffers from these harms, that really always depends on the problem. It is sometimes groups as defined through certain protected attributes, such as in certain contexts by the law, through attributes like race, gender, age, sexual orientation, religion, nationality. So it depends on your application scenario pretty much. But it doesn't necessarily have to be a group defined by these attributes. In the voice recognition example that I provided, if you have a smart speaker and it doesn't recognize your voice as a non-native speaker, that's not necessarily a protected group. And then very important point also here on the right is, I hope that's readable in yellow, intersectionality really matters. When you consider groups separately, for example, you might be fair towards the attribute gender, and you might be fair towards the attribute race, but that doesn't mean you're fair towards all overlapping groups you could create from those. So that's commonly what people refer to as intersectionality, and not considering
Roman, can you hear us? We lost audio.
Maybe he needs to log in.
Roman, are you able to hear us? We are not able to hear you. Let's see if I can unmute.
can you hear me now? Sorry.
Yes. Now we can hear you.
Sorry, how long was it off?
No, we cut you off immediately.
Okay, fantastic. Yeah, sorry for that. Must be my microphone. Yeah, let me jump back into this. Yeah, it was just at intersectionality, so can continue from there. So the sort of the knee-jerk reaction that people jump to when they hear about this the first time, and I was the same way, is that well, if there are issues with these groups defined by such attributes, why don't we just remove this information? Usually in machine learning and artificial intelligence, you have a training data set that includes things like race, gender, age, all these attributes. Why don't we just take it out? And that's actually there's a term for this. It's called fairness through unawareness. If you don't know about these things, then how can you be unfair, right? But this has been shown to be insufficient, unfortunately, because in many data sets you have redundant encodings. That means that other attributes, other features in your data set actually are predictive of your protected attributes. So for example, redlining is a good case because it causes some of these things. So on the left here, we have a map, found one of Philadelphia, but there are many others. And they've literally marked in red the least desirable neighborhoods because that's where you had a highest percentage of Black residents, and there was systematic discrimination. I'm sure most people here, due to your backgrounds, as you explained, are familiar with the term redlining. So due to this, to this day, as a consequence of this historical discrimination, you still have, for example, zip code is fairly good. You can be fairly confident in predicting somebody's race even to this day. And especially if you combine zip code with other attributes, you can be even more confident about this. So fairness through unawareness doesn't quite fully work. You essentially just become blind towards whether you're unfair or not with your model. And that's probably the last thing we want to do. We want to at least be aware of what we're doing such that we can prevent such systems from getting deployed and used against and used to harm people. So the opposite of unawareness is awareness. So to be aware, we need to sort of measure what's happening. And for that, we have various kinds of fairness metrics. But broadly speaking, in the machine learning fairness community, people look at 3 kinds of fairness. That's individual fairness. So you're thinking about, can we treat similar people similarly? But that would require some sort of similarity measure. And that is also something you have to construct. So you sort of infuse your own bias in how you create that similarity measure, and you can get it wrong. So it's not something I'm going to talk about. I'm going to stick to the 3rd point here, which is group fairness in the top right. The other option that we'd have is counterfactual fairness. So sort of, for example, in the applicant screening scenario, I might say, okay, my application was rejected. I did not get the interview. Well, what would have happened if I was 10 years older? Or what would have happened if I was of a different gender? What would I have been accepted if I was female? It's a reasonable, I think, intuitive way of thinking about fairness, but from my perspective, it's a little bit less realistic to assume that I would have been exactly the same person if you can change certain attributes about me. So it comes with certain caveats, and it's less well studied than group fairness. In group fairness, we literally just define groups based on certain attributes. Usually that's sensitive features, but you can define a group however you want. And then you compare the outcomes, or you compare using certain metrics, what happens between these groups. And if it is an appropriate metric, then hopefully you're able to somewhat measure whether your model is fair. So that's the high level idea. And if there is a disparity between groups, then you might conclude that a model is not fair or less fair. We'll see an example of this on the next slide. I just want to point out the issues with that right away before we get to it. And that is that fairness, like you've said before the talk, and like we've seen here as well, is it's a societal construct. So defining this in a quantitative way will always omit certain aspects of fairness. In certain scenarios, we may not be able to come up with a proper metric at all, and perhaps it's better to not build a technological solution. It's something to be considered. And finally, metrics are numbers at the end of the day, and you can't represent every concept that may come up in law, like that, like justice, for example. Okay, so I have a hopefully simple scenario here, which is the applicant screening scenario for a job from before. Here we have a little table with 200 people who applied for this job. We have some input data that tells us whether they were hired or not. And we take this sort of as an indication of whether the candidates were qualified or not. So we end up training a model on this, and then our task for our machine learning model is to decide whether or not an applicant should be invited for an interview. Disclaimer right here, that a decision to have the historical decision whether somebody is hired or not to indicate whether they were qualified or not is obviously one kind of bias that we're already putting into this model. how bad that is unclear for my fictional example here. So what you see in the on the left side here, with invited, not invited, this is actually the predictions my model makes, and then also the outcome that happens. So for example, the people in the first row here, they are getting invited for an interview, these 30 plus 28 people, whereas the people in the lower row are not going to be invited. And column-wise, these are the people who got hired historically in my data set, and these are the ones who were not. Okay, so in machine learning, generally people call these true positives, false negatives, and true negatives. So I just keep this up here as a little bit of a cheat sheet, because unfortunately we need these terms quite a bit to define various kinds of metrics. Now, like I said, in group fairness, we try to compare these metrics across groups. So I've just broken this down by 100 people of group A and 100 people of group B. In practice, that may be, for example, men and women. If this was a better example, I would have included non-binary as well. It didn't quite fit on the slide, to be honest. So that's my only sad excuse here. But in a real scenario, you would definitely want to factor that in. Otherwise, you're dropping candidates and thereby already treating them unfairly by ignoring them. All right, so we can see a few things here. We can see that overall, there are already more men with the qualified label than women. Perhaps this is an example of historical discrimination that happened in this case, but it's a fake data set, so I don't want to spend too much time on that. It's more about defining the metrics such that you have an intuitive idea of what kind of metrics one can create. And one of them that is very commonly used and quite famous is demographic parity. So for that, we would really just think about the outcomes. Outcomes is our first row here, whether somebody was invited for an interview or not. So we would think about between these groups is the proportion of the opportunity we extended, in this case, whether they were invited for the interview or not, the same across the groups. And it's not close here. We have 26 people total on the left side and 32 on the right. So it's, yeah, it's not close, but it's not too bad either. It's not like nobody was invited from the other group. So there's some disparity. If we make the assumption that both applicant pools are about equally talented, which is probably not an unreasonable assumption, then perhaps this is not a fair model. Now, other metrics that we could look at are true positive rate. For that, we really want to look at the true positives divided by all positives. So that would be the first column. Up here's the cheat sheet if you want to take a quick look. So true positives divided by the sum of true positives and false negatives. So that would be 10 divided by 20, so half, 50%. And on the other side, 20 divided by 40. So they're actually very even between the two groups, and true positive rate parity would be satisfied. Now, why would you take this over the other metric? If you've paid attention, you've noticed that we've actually only looked at the column with label 1 here. We've totally ignored the other column. So this is something that you might want to use when it's very important not to have false negatives. False negatives, or there's an equivalent definition on the next slide for false positive rate parity, which looks at the other column. But sort of the two mistakes that you can make is false negatives and false positives. So in certain scenarios, it's really bad if you have those. For example, in the risk score criminal justice criminal sentencing scenario, you may not want to send somebody to jail who is actually who could just go free and yeah. Because,
so Roman, we have a question.
Yeah.
Sylvia, do you want to? So is there a recommended process or model for determining the types of group to consider in any given technology? So what is the rationale behind choosing the groups or creating these groups?
Yeah, so one way to start is looking at the legal situation. Certain, I'm not a legal expert, so don't quote me on this, but certain scenarios force you to be fair towards certain groups as defined by protected attributes. So then you have to follow that. Whereas, as far as I know, there are other scenarios where you're not allowed to use those attributes at all. It's definitely important to have somebody in the room when you're planning such a project who actually understands what the situation is for your concrete application domain. Other than that, it also depends on what you have data about, what you expect your user base to be. If you build a solution that is only targeted at men, for example, then it doesn't really make sense to be fair towards women, because there's no point in doing so. But it's really case dependent. I have there's after yeah, a few slides later, there's a paper that's referenced, and I'm happy to share the list of all the links that show up in this, obviously. That a paper called Co-Designing Checklists for Fairness by some of my colleagues, and they have a really exhaustive list of things you should do when you want to build a fair solution. So that also goes into detail on what kind of groups you may want to consider. Does that sort of answer the question?
Thank you. Mm-hmm.
Okay. So yeah, so if you really want to avoid making certain kinds of mistakes here, one mistake being false negatives, the other one being false positives, then you might consider true positive rate parity or false positive rate parity, which is the other one. Parity between those would mean that you just make the same kind of mistakes for both groups in this case. Very importantly, this can generalize to more groups as well, especially if you have intersections of groups as defined by race, gender, age, you name it. You may have many more of these tables. And you can also have multiple of these applied. So equalized odds, for example, is a criterion that consists of both true positive rate parity and false positive rate parity, and is fairly known in the machine learning fairness community, at least. Now, I want to talk a little bit about, now that you have like a rough idea of what metrics sort of look like, or how you would analyze the data, I want to spend a little bit of time on how our model, how certain kinds of biases come into the model in the first place, and where we have a lot of influence on how to prevent that. And for the much more comprehensive version of this, I recommend watching a video by two of my colleagues, Jen and Hannah, who have an on-demand webinar on the topic. And they walk sort of through the same topics, but in much more detail than I have time for here. But I want to give you an idea of what this looks like anyway. So when you look at how a team builds a machine learning model and how that gets into production, that usually goes into the AI development and deployment lifecycle. This is intentionally a cycle because usually as you build your solution, you deploy it, things change, you may have to, you may get new data, you might retrain your model, redeploy it, things might change, the environment changes. We have it right now with this pandemic. The situation just changed everything. Perhaps our data is not as relevant anymore in the deployment context, so we have to redeploy. But in each of these steps that you see around the circle, you can actually infuse your own kinds of bias into the resulting model, and that can have drastic consequences. Yeah, I'll name an example for each of the steps because we don't have a lot of time, but here's one to start with, task definition, which is usually where you'd start. That's all about deciding what you're actually going to do. A bad example for this is this paper by Wen Zhang, I think from 2016, called Automated Inference on Criminality Using Face Images. Essentially uses face recognition to predict whether somebody will commit a crime. So you're only using somebody's face to say whether they're going to be a criminal, which is, I think we can hopefully agree on, a great deal of harm for the misclassified people, and quite questionable task design at best, and a task that probably, frankly, should be avoided altogether. I say this a lot, and people smile when I say this, but one really shouldn't be afraid to simply abort some projects in this stage. There's no harm in doing so, at least none done yet, before you deploy a solution. And realizing certain harms can be very helpful. So things that you might do against that is clearly define what you're trying to do, thinking through what kind of harms might result from such a solution, and really documenting all the decisions you consciously make. And that applies to all of the steps here. When you document everything, then 3 months from now, 6 months from now, when you go back to it, you might realize, okay, we've actually thought about this before, and this is why we decided one way or the other. Another thing that I find quite useful is thinking through whether somebody else has tried this before. That's why I keep my list of questionable use cases, such that you can find that on my webpage, and I'm happy to share that afterwards. But you can sort of see what other people have tried and in which ways that has gone wrong. And really, none of this is about shaming companies or researchers or such. It's about making sure we don't repeat those mistakes. As you've heard before, I've mentioned my own company in the beginning as well. Yeah, data set construction. So that's how you get your data, you label it, you pre-process it, you collect it. That in itself, that is sort of where most people talk about bias. With the data, it might come in through societal biases, historical biases. But even by cleaning a data set, you might introduce new biases. And a great example is from Boston, where I just moved from. They have the Street Bump app, which is pretty useful. You essentially turn it on your phone, and when you drive over a bump, it reports that to the city, so the city can come and fix the pothole. In 2020, this is certainly a great solution. This was launched in 2011, though, so not a lot of people had smartphones yet. And they quickly realized that most of the data points they were getting came from affluent neighborhoods. So if they had just blindly followed the output from this, from the data they were gathering, they would have just fixed all the potholes in those affluent neighborhoods, but not in the less affluent ones. So you can really skew things by making certain assumptions there. Again, if you document all your assumptions, have a diverse team that can potentially see more of the issues in your assumptions than you yourself could, that is a huge help. Yeah, there's a big effort across the entire community to sort of come up with a standard for data sheets to document all these assumptions, in case you are more interested in that. Now, this is the model definition part is where most machine learning practitioners would get the most excited about, because this is where you define your model. But again, depending on how much you know about machine learning, you're infusing bias again here. If I only know about linear models, then the simple case here that's displayed can already ruin the entire task. You have some data points here. I hope the lighter and darker colors are sort of distinguishable. This is sort of the majority of data points. You have some have a different label than others, so you can actually linearly separate them with this red line, which would kind of be the decision surface for our model. So if a data point falls on one side of the line, it will get a different outcome than the other side. By outcome, I mean things like, do we invite them for an interview? Whereas for the minority, same thing, you can linearly separate the points. Some fall on one side, some on the other side. But if you combine the data points into the data set, which our model is trained on at the end of the day, it's not quite as obvious anymore. And the way machine learning works is you have some sort of objective function. You want to maximize some sort of accuracy measure. And if one group in the population is much bigger than the other, then the solution will probably approximate something like this line that is the solution for the majority, because more data points weighs heavier towards what the solution is. So what kind of model you specify has a big influence on the outcome as well. There are certain assumptions we make when building our models, assumptions on the objective function, on the structure of the model. And a linear model here, for example, is one of those assumptions, and it's just not enough. The good news is, if you've done everything all right so far, then the training process can't really hurt much, because you're just running something on some compute somewhere, and everything is predefined. So you hopefully can't get anything wrong here. But once you actually have the model at the end of this process, then you have to test the outcome. Does it actually do what I want? This goes back to the metrics that we've looked at. Hopefully by this point, you have defined some metrics that are appropriate, that represent something close to what you think is fair in your application scenario. And you can test with an held out data set, so not the data set that the model was trained on, but a separate one, and validate that your model does what it should do. The thing on the right here is, again, screenshot from the Compass article called Machine Bias from ProPublica, because they were essentially arguing is that the Compass risk assessment system is unfair because they use different metrics. The ProPublica folks were looking for false positive and true positive rate parity, whereas North Point, the company that behind Compass, was more focused on predictive parity, a different metric, and they were defending themselves, while ProPublica argued that the system is unfair, and they have good arguments for that. So it really matters that perhaps at this step you have an audit with people who weren't involved in building the model, just to understand how they perceive the outcomes from your model, and not move further to the next step, which would be deployment. Oops. Because that's when people would actually see the harms. The most important thing for the deployment process is that you make sure the deployment context is the same as the kind of context that you have tested with in the previous step, and also the same kind of data that you had when you trained your model, because you might see this map on the right side here. I hope your screens are large enough and it's somewhat visible, but it shows you the distribution of geographically identifiable images in the open images data set. Now, if you trained a model, say, to recognize cars or any kind of object or people with that data set, then mostly you would have trained it based on images in North America and Europe. There's less than 1% of the images come from China and India, and you know that they have a lot more of the population worldwide than 1%. So if you then go with this model that is trained on this context and apply it in China or India or Africa here, if you look at the map, is basically underrepresented, then that may not make sense. Especially with faces, I think it's quite intuitive. So that's always something to consider. Again, documenting these sort of choices, where the data came from, is very important. Once your solution is deployed, you need to check for feedback loops, use your feedback, and sort of see what happens. The failure case here on the right side is hotspot policing, in case you're familiar with that. If you take the number of arrests, for example, as a signal for a crime, then you may discover a map like this with lots of hotspots of crime. You might send, as a reaction to that, you might send more officers to these spots. And inevitably, you'll end up discovering more crime, because where officers are, that's where they can discover crime. And then you've sort of fed the feedback loop, and you'll keep discovering more wherever the offices are, and in return, the other areas where there's no detected crime will not have any officers, and therefore no detected crime. So sort of the mistake here comes from the objective and the assumptions you've made for the model, but you need to be monitoring for feedback loops like that. And this here is the page that I was referring to before, which is sort of the checklist paper by some of my colleagues from Microsoft Research, co-designing checklists to understand organizational challenges and opportunities around fairness in AI. If you download the PDF there and go all the way to the bottom in the appendix, they have the really comprehensive checklist, which I recommend, which goes through all of these stages in detail again. There's somebody trying to say something?
Yes. So Roman, one question on the previous slide.
Yeah.
So this is question from Sylvia. A lot of risk I see is the aggregation of GIS data with other data sets. Do you see GIS as a particular risk in ethical considerations?
Yeah, all data sources carry some risk. I think it really depends on the scenario too. Right here, it was predictive policing, which a lot of people would argue is a very high stakes scenario, regardless of what kind of data you use, because people can be severely affected by harms created through these systems. There are definitely scenarios where geodata is super useful, and I keep thinking about this is the context that I'm familiar with, but Microsoft has a AI for Earth initiative where we sponsor lots of, I think it's mostly nonprofits or only nonprofits that are trying to do good things with geodata and not only geodata, but other applications. So it's not necessarily like a good and bad decision. It's not bad and inherently bad if you use geodata, but the problem here is the established feedback loop, and that's independent of whether it's geodata. But it's certainly something to consider, like what are the possible feedback loops? Could we be sending people to the same location? Should we be using geodata in this application at all? Yeah, I don't think I can give a more general answer without knowing a specific application scenario, sorry.
Yeah, Sylvia, do you wanna?
Yeah, so I guess, no, this isn't confidential information. As you know, government has law, sunshine law, so anything I share in this group is not confidential. Just saying that. We had a opportunity to share we have an incredible GIS data set here in King County that people from all over the country hire us to do work, other governments. And we had an opportunity for an unnamed insurance company to buy our GIS data to study claims and the prevalence of claims within certain communities, which could be taken as an effort to identify certain types of healthcare problems, as we all have seen this, I think, quite predictable but unfortunate result of the lack of taking the complaints of African Americans seriously in the medical field, or the lack of access to medical care has disproportionately led to increased deaths in the African or in the Black community. And so it could have been, seen as a good thing. On the other hand, there is a risk that, it would I think there's a double-edged sword with all of these things that I see, where it could have been used to deny claims based on, so there was a question about whether there were too many claims coming from certain areas. And so, I decided that it wasn't an appropriate data set for King County to share. So kind of along those lines, I'm wondering, given the fact that redlining, you already acknowledged the effect of redlining still exists, that sharing GIS or GIS data can have that double-edged sword.
Yeah, definitely. I can totally see how this may work out harming people, as you hinted at. It really depends on the scenario. In many cases, I'm sure the companies that could use it already have the data too, or they have other means of getting it, even if government agencies are not able to provide or don't want to provide it to them. It takes a lot of courageous people in the room then to perhaps stand up and say, no, this is not what we want this to be used for, which may not be what happens everywhere.
It is hard to know, though, because you have to assess people's intentions.
Yeah.
And so part of me wonders, how do we do that?
There's some thoughts along the same lines regarding software, where people are sort of thinking about a Hippocratic oath not to do any harm with the things they're building, or then in regards to software licensing, that people can only use certain software if they promise not to do any harm with that. And it's a very controversial topic. There are very good arguments from either side. I don't claim to have a good answer.
I definitely appreciate that. I just wanted to ask because I feel like this is where I should ask the question.
Well, I think that sometimes we have like lawyers and stuff in the group too, kind of for those exact reasons, because then you look at liability issues, right? Then who's held accountable because this is what they said they're going to use it for? Is it the responsibility of the person with the data to give that a while, to assume the worst at the same time? And I think that's why it's great to have multiple different people, because I think this is where you start bringing in the law 100% into some of these conversations, or like what Roman said earlier, because these are so case-by-case basis, it's always good to have somebody in that conversation on every one of these projects. Because, as an engineer, you're only looking at the project per se, and you're going to hear what they say. And of course, yeah, that makes sense. And you might need to have someone at the table on all these conversations, say, what are the implications? How do you prevent yourself from some of these hold harmless areas? So I think that those are things you definitely want to like what they said earlier, bring the right people to the table, because this becomes more than just a technological advancement. And every company has become a tech company now too.
Yeah.
So.
In fact, you could not have come up with a better introduction for my next slide.
You're welcome, Roman.
Which is this one. And I'm not going to go into detail with all of these because we don't have that much time. I've given a talk about just this paper, Fairness and Abstraction in Socio-Technical Systems, which is actually written by a law professor and a few others, where they think about the kinds of things you encounter when trying to bring together fairness and machine learning. And they stumble across fairness being something socio-technical at every step. For example, the framing trap. So it's all about things, pitfalls, things you can get wrong when you try to build fair machine learning solutions. And framing is all about, have we considered the context? What is the frame of the system in which it's used? And for example, for the risk assessment with Compass, it's very easy to argue that this has not been assessed. The risk scores are not the verdict by a judge at the end of the day. They're not the sentence. The risk scores are given to a judge who may then, while sitting in the courtroom and looking at the defendant, decide, well, no, I know better than this risk score. I won't look at it. Or, yeah, this risk score makes sense. I'll do what it says. So there might be biases that we haven't even uncovered yet, because we have looked at the wrong frame of reference. So that goes back to that whole fairness being socio-technical, like you said. I've briefly touched on the ripple effects through the feedback loop before. Those things are to be avoided. The paper describes it much longer and with great examples than I can in the short time I have here. But the one at the bottom, I think, is almost the most important one, which is the solutionism trap. Perhaps in certain high-stakes scenarios, it's best not to build solutions at all. And it's something we shouldn't shy away from. To stay with the law and fairness, there's yet another great paper, which I recommend people take a look at, on the legal compatibility of fairness definitions, by Zhang and Rajiv from the Partnership on AI. And they sort of try to bring together the communities while acknowledging that law is something much more established than the fairness community, and where there are sort of clashes and where things need to be worked out. Because from a legal standpoint, motive, intent, causality, these are all things that have a meaning that in fairness, we perhaps frame incorrectly or inaccurately through correlations that may not quite work out the same way in the legal context. So I think there's going to be a lot of interesting court cases over the next so many years, but it's just acknowledging that there's work to be done. And another one that I found very interesting is that from ML Fairness, if you read those papers, you find that everybody focuses on minorities and marginalized groups, whereas in anti-discrimination law, the cases are often the other way around. You have somebody from the majority, usually white male plaintiffs, seeking protection from policies that are trying to, well, it says benefit minorities. I think I quoted that directly from the paper, but or even trying to even things out. So from our fairness perspective, we should really think about, are the tools we're building, are the solutions we're building going to enable more of this, or should we be careful with that? And then the last one here is something that we already heard earlier. In which context are we actually allowed to use these features or not? So this is everything that I wanted to talk about in terms of fairness in general. I want to just, if we have enough time, perhaps spend 3-4 minutes on how this relates to my daily work, since I may be interested.
So we have one question, Roman, and then we can go there.
Yeah.
So one question from Kyle. Kyle, do you want to?
Yeah, just I guess a basic question. With computing power becoming cheaper and cheaper, who's to say, what if somebody disagreed with the parameters, the definitions? Could they analogously do a git clone, set up the exact same model you have, tweak it to their own nefarious purposes, and you do all the work and they do the unfair stuff anyway? Is there a solution proposed or some sort of legal thing that would ensure that they use the just model, the fair model?
Right. So assuming I put my data in my model on some sort of file share, let's say GitHub, and I say this is my model I use now for image detection or whatnot, and it's fair because I've made sure of it. And then somebody else comes along and says, well, I like a different definition of fairness, clones it, uses a different metric to optimize for, and ends up causing harm. That's possible. For that reason, we're very careful in kind of the examples the curated examples we put online. If you go to our code repository, I think it's a few slides from now. There's a link. If you just search for FairLearn, you'll also find that there's a notebooks directory where you can sort of walk through a curated example. We're very careful on how we frame this, and kind of try to include the decisions that we consciously made on doing something or not doing something. I cannot directly stop anybody with bad intentions from doing things, but all we can do really as the provider of tools is, I think, try to educate people as much as we can, and perhaps provide hints to them as to when they might be doing something that's off. It's a difficult question. I think for most applications, you wouldn't really have the full model or everything public. For example, any AI system built by Google or Microsoft or any company probably wouldn't have the data at least publicly available, right? So it's, to some extent, it's prevented like that, but I do feel like there's sort of a vacuum to some extent in the legal sense on what is required of the people building models that would sort of provide a clear guideline on what needs to be done before you deploy a model, or otherwise this is something that the police will come after you or something like that.
Yeah, I think Hisham and Sylvia want to also
go ahead.
Try and answer this question, Kyle, for you. Hisham, go ahead.
Yeah, first of all, thank you very much for that. But I just wanted to chime in for that because, as I said, I worked a lot in the fields of cybersecurity and AI within that, and mass surveillance. And just so you know, there has been like a lot of attempt to create until now. We don't have any legislation like we have here in Toronto. There's an initiative by the city of Toronto for AI, a law of AI. There's something in the state of California, for example, the new privacy agreement. They have some rules on how these algorithms should be done, specifically the ones who are for like surveillance or the cameras or anything like that. So these are good. GDPR has done some part of it. It's just lacking. But what I know also is that Microsoft, the AI labs in Microsoft in Seattle, I believe it's at, are doing a lot of studies around that and how they're creating a lot of research and documentation, because I don't think the legal system can understand. There's a lot of technical stuff that goes in, and mostly the legal people do not understand that. So it's as I said in the beginning, it's a negotiation that everybody has to be on the table. And what I know is like Microsoft is bringing a lot of people from many parts of the conversation and putting them all together in a research, in a big research, and trying to create like kind of rules of what's an ethical algorithm, or what's a fair AI application for that matter. There are also some others. I'm not just saying here Microsoft. I know that there's some also initiatives from Google and Amazon, I believe, and some of those. So there are initiatives. There's nothing yet here, but there are initiatives. There are also some kinds of, here in Canada, we're trying to create a new version of PEPIDA, which is also, again, a privacy, but it also might include some legislations on how to do that. But I think it's still a baby, and there's a lot of things to learn still from a technical point of view, and from everything, like also from like a legal point of view. But there are initiatives. And again, as I said, places like Center of Ethics here in Toronto, there's a lot of places also I know about in the United States and all doing that. So I believe we're getting there. And I believe these kinds of conversations are very important for that matter. Also, I would like to just point out the last thing, that the Azure AI, they have implemented new tools that's called cognitive services. Using cognitive services, like I've been working on them, they are mostly helping in mimicking human behaviors more than the normal, straightforward, logical AI. And I think that these tools like this in the future are going to help more into making an AI more of a human, or have more empathy or whatever. There's also researches about empathetic AI, or they call it EI, or synthetic AI, whatever. There's a lot, but until now, it's all still experimental.
Yeah, just to echo one of the things that you said, we do in fact have a lot of people in this area in Microsoft, but it's really crucial that it's not people from the same sort of group that are participating in the conversation. That's why I really appreciate that people from various backgrounds are here today. I didn't have all the legal context that you just provided, for example.
Thanks. Sylvia, you wanted to share some couple of points.
Yeah, so in the last year I've done research going back to the Reconstruction era in the United States during the 1880s after the Civil War, where the Supreme Court was deciding cases such as Plessy versus Ferguson. As we all, well, many of us know, that's the case that allowed separate but equal schools. So, allowed the United States to segregate our school system. And in those cases, the proponents of segregation were very, very clever in how they twisted in otherwise what seems like an otherwise very good argument for equal rights, which is to propose that the law be colorblind. Unfortunately, this is a very this is an ongoing issue here in Washington State. In fact, in November, we had an issue on the ballot, which the proponents of overturning the ability of our government to address the disparity in government contracts was overthrown based on these colorblind philosophies. And the problem is that being colorblind, you cannot then say that there are issues with color,
yeah,
or differences within groups. And so that's the current state of the law. But I haven't seen, going back to what before that, we were talking about how, say, Microsoft or other companies would enforce their ethical policies upon folks using their technology platforms. So I was just kind of wondering, you know, can you take away licensing rights? I haven't seen anything in the licensing agreements I've looked at with Microsoft, or exclude, you know, kick partners out if they have been, you know, I think there is a stick that can be used by companies for enforcing their own ethical rules once they're put in place. But I haven't seen that come to fruition yet. My comments.
Yeah, so within Microsoft itself, for example, I know that we have to have certain reviews if you want to deploy a machine learning system into production. So as part of that, a lot of things are covered. I don't know to what extent the expertise for that is there in every company. It's probably something to doubt. I do think transparency helps in a lot of these cases. If you, I have it with the Fairlearn toolkit after this. If everybody were required to publish or voluntarily published a lot of aggregate statistics on how their model treats people, that first of all creates awareness within the people, the group of people building models, but also exposes yourself sort of to the public, and you better make it right and explain your decisions ahead of time. But I guess that's wishful thinking at this point.
I think that companies could very easily, well, not necessarily in the city of Seattle, but in many jurisdictions, lobby for legislation to protect them if they do find flaws in their algorithms and fix them. Anyway, I'll stop. It's your talk.
Thank you.
Right. So I just want to show you a very brief, not demo because I screenshotted everything, but sort of like a demo of what I'm doing in this area in my day-to-day work, since it's related. So I work on the Fairlearn toolkit. This is a toolkit with mostly two components. One is the assessment of unfairness, and the other one the mitigation of unfairness. In practice, what you do is you evaluate various metrics, some of which we've looked at today, with visualizations as an additional bonus. Or then if you find that your model doesn't quite perform the way you want it, or is unfair with respect to, for example, demographic parity, you have the mitigation component. You can specify your criterion or multiple criteria and mitigate your model using a variety of techniques. They have their pros and cons, which I won't get into, but if anybody's interested, please just reach out afterwards. I'm more than happy to talk about that. So in practice, what that would look like, you run your code, it pops up a dashboard. In this case, we've provided a few sensitive features with our data. Here it's binary gender because in this specific case, we didn't have a non-binary, unfortunately, but it's just for illustrative purposes. So you can pass any sort of groups in here, and you can select however many you want. So that's basically to define the groups that you run the metrics against, and you have to define what your accuracy metric is. So that's how you measure generally how well your model performs. This specific case that I ran here was a binary classification case. So just like the hiring application screening scenario that we talked about earlier. So that's why binary classification is 0 or 1, invited for interview or not. Let's just select accuracy. And then you get a view like this. Now, depending on how large your screen is, you may or may not be able to see a lot here. Pretty much it's divided into two sections. One is disparity in accuracy. So You have a row here for every group. The first one is male, the second one is female, as a group as defined in the previous screen. And you see how the accuracy with respect to the training data you provide is different. So here I have 79 versus 92% accuracy, so there's some 12% difference. And you can see how exactly that came out, because accuracy just means that you were wrong, but not whether you underpredicted or overpredicted. So you can get an idea of what's going on here. And then the lower half is disparity in prediction. So here you're purely looking at outcomes and not at all at the training labels. So whether somebody was hired in the past or not is irrelevant now. But we find here that male candidates have, it says here selection rates, that's invited for interview, 23% of the cases, and for female only 7%. So there's quite a bit of disparity in that right here. This would basically be your demographic parity that we've looked at earlier, and you don't have the state of demographic parity. You have quite some disparity here, 16% almost. Now, after seeing this, your model's not quite the way you want it, perhaps. You can run various mitigations. I won't get into that now, but essentially you're either post-processing the outputs of your model or you're adjusting the objectives in model training. We've done this and have an entire different set of models. Is now a comparison of many kinds of models. The one that we looked at in detail in the previous slide is back up here in the top right corner. And then these other ones sort of represent a Pareto curve along the axis of disparity on the y-axis. So the further down you are, the better. That means no disparity. Oops, sorry. And the further to the right you are on the x-axis, that means the higher your accuracy. So in an ideal world, you'd want to be in the bottom right. And then you sort of have to pick your poison. Do you want to have lower disparity, so that would be further to the left along the curve, or higher accuracy? And you can see that without sacrificing much accuracy, you already get pretty low disparity. So perhaps, I apologize, perhaps something along the lines here would be a suitable model to choose. And then you can click on these and go back to the previous view and analyze individual outcomes per group. So that's kind of the visualization component that's easier to show in this presentation. We're on GitHub. This is all openly available for free. It's an open source project. And we're trying to build a community around this. So anybody who wants to contribute or use this is free to do so. We're always looking for feedback if you have any. Yeah, I have on the last slides, I have some ways of reaching out to the project in general if you want to provide feedback or you have use cases that aren't covered here. But overall, I want to reiterate, since I've now shown you this tool, fairness is still inherently a socio-technical challenge. And just because FairLearn is a tool that sort of can visualize some of the fairness accuracy trade-offs and perhaps mitigate some unfairness if you specify the options right, that does not mean that FairLearn alone is a solution to your problems. If you want to build fair machine learning systems, it is perhaps one piece of the puzzle, but that puzzle is a lot more complicated than just FairLearn. And the middle point here is that depending on your distinct application scenario, you have to choose the right fairness metrics, and perhaps they don't capture all the aspects that are relevant to that scenario. Yeah. So essentially, you have to be really careful what you're doing. Since this just came yesterday, I added the slide today. Microsoft released a whole collection of resources related to responsible AI that includes more than just fairness. But if you search anywhere online for Microsoft Research Responsible AI collection, you'll come across this link. Various useful things there, including that fairness checklist that I referred to earlier, as well as the webinar by my colleagues, Hannah and Jen, and our FairLearn toolkit is also on the list. And then finally, that's just links on how you can reach out to the project or directly to me. Yeah, feel free to do so. I'm always happy to interact with people.